Welcome all. This session is a continuation of the previous session 12.2, Rectilinear Kinematics and Continuous Motion. But in this short session, what we are going to focus on is the constant acceleration relations. The application of the constant acceleration relation are basically for those problems where the acceleration is constant. So for example, if we look here, if the position is given as a second order function, then its a derivative with time is going to give us the velocity, which is a linear equation, and the derivative of the velocity with respect to time is going to be a constant. So this is why the acceleration is constant with respect to time. And as we are going to discuss later in this session, the example of a rocket moving upward against the gravity and then reaching to a point where it stops and then falling downward until it hits the ground, this is a motion under a constant acceleration, which is the gravitational acceleration. In another example, we can have either a car moving in a rectilinear path, but the acceleration of this car is constant. So, for example, we can say that the acceleration is 10 meters per second. And that's it. Now, let's try to derive the first constant acceleration relation, which is velocity as a function of time. But before I start, let me point to something important over here, which is that we are going to call A as A sub C, which is a constant. So, to start with, we will start by expressing the acceleration AC, which is equals to dv over dt. Now, if we do the cross multiplication, we will get dv equals to AC multiplied by dt. Now, if we take the derivative of this, we are going to derive from we are going to take the integral from v0 to v for dv, which is equals to the integral from 0 to time t for AC multiplied by dt. Now, clearly, if we take the derivative over here, if we take the integral over here, we will get v going from v0 to v, which is equals to AC multiplied by t from 0 to t. Now, if we substitute, we will get v minus v0, which is equals to AC multiplied by t, which is, in another word, v equals to v0 plus AC multiplied by t, which is the famous constant acceleration relation between the velocity as a function of time. We can always point that, for example, the right-hand side, if we write this in a vector notation, is positive, while the left-hand side is negative. The second constant acceleration relation is for the position as a function of time. And to start with this, we say that the velocity is equals to the change in the position with respect to time, which is indeed, as we derived in the first equation, equals to v0 plus AC multiplied by time. Now, we can have ds equals to v0 plus AC multiplied by time by dt. And then we can integrate from s0 to s for ds, and then integrate from 0 to time t for v0 plus AC t dt. Now, we are, from the left-hand side, we are going to get s minus s0. From the right-hand side, we are going to get v0 multiplied by t, plus this one has a t, so it's going to have 1 over 2 AC multiplied by t squared, which we commonly know from physics, this equation, S is equals to S0 plus V0t plus half AC multiplied by t squared. Again, this equation can be written in a vector notation where the right hand side is assumed to be positive and the left hand side is assumed to be negative. Let's move on to the third relation. In the third relation, we will start with the independent equation of time. If you remember it, v dv equals to ac ds. In this, we are trying to express the velocity as function of position. So to continue, we are going to integrate from v0 to v for v dv, which is equals to the integral from s0 to s for ac ds. Now, if we do the integration, we are going to get 1 over 2 v squared minus 1 over 2 v0 squared, which is equal to ac multiplied by s minus s0, which again, a familiar equation, v squared equals to v0 squared plus 2ac multiplied by s minus s0. Again, we can also write this in a vector notation by also specifying the direction where the vector is positive. For example, the right hand side is positive and the left hand side is negative. Now, let's have this example. As I mentioned in the beginning of the session, in this example, we are gonna have during a test, a rocket is traveling upward at a 75 meter per second velocity, and it is when it is at 40 meter, that's a 40 meter, look downward over here, that's 40 meter, the engine failed. So what happened is that the engine, the rocket start to move upward, and then until it stopped, and then it fall downward. Now we want to determine the maximum height, SP, reached by the rocket and its speed just before it hit the ground, right there at point C. We would want to neglect the air resistance. Now, to solve this problem, what we are going to do, we are going to first start by the maximum height. So we want to know the maximum height. Now, what you need to understand is the following. Here, the velocity at A is upward, just when the engine failed, and its magnitude is 75 meter per second. It is pointing upward, and this is basically the location of time equals to 0. Now, what we are going to say, we are going to say that the maximum height reached, which is measured from here, this is our reference, and upward here is positive. This distance, which is the maximum height, is called SP. SP is because the point here at this position right here is P. Now, also, we understand that the rocket will move upward until it reaches point B, and when it reaches point B, it will have a velocity VB, which is equals to 0. Then it will start moving downward. Now, what is important here is that when the rocket is moving upward during this journey from A to B, the rocket is moving upward, so the direction of the velocity is upward, while the acceleration g is downward. And for that reason, since the velocity is opposite to the acceleration, as you agreed, then this acceleration is going to be negative, minus 9.81 meter per second square. That's AC. Now, for the second part, from B all the way to C, the acceleration is also going to be negative. Why? Because in this way, in this part of the problem, the positive direction of the displacement is upward, while the body is traveling downward. So the acceleration would have to be also negative. And what are we going to do for the first part? We are going to consider points A and B. So we are going to assume again that upward is positive. That's our direction. And then we will write the equation VP square equals to VA square plus 2AC multiplied by SB minus SA. As you see, this is a constant acceleration equation. And the reason why, because the acceleration in here and there is constant. It's one number. So if we substitute, VB is equals to 0. And VA was positive upward, 75 meter per second square. And then we have the constant 2 multiplied by minus 9.81. And then we have the position SB, which is the unknown, minus 40. 40 is the initial position from here to there. Now, so by doing the calculation, we will find SB equals to 327 meter. And this is the first unknown. Now, for the second part, which is the velocity before it hits the ground at point C. Where is point C? This is point C. Now, we will only consider this portion of the motion right from here at point P all the way down to point C. Now, if we look here, the dynamic state at point B is known. We know that VB is equals to 0. We just calculated that SB is equals to 327 meter. Now, we also know that the acceleration, as we discussed before, is going downward, and it is minus 9.81 meter per second square because it is opposite to the positive direction of the displacement. And now we can write down the equation similar to the previous one, again, assuming that upward is positive, but this time between VC square and VB plus 2AC multiplied by SC minus S. Now if we substitute, we know that VB is equals to 0 plus 2 multiplied by minus 9.81 multiplied by SC is going to be 0, while SB is going to be 327. Now, if you do this multiplication, you have a negative, just to show it, you have a negative here and a negative here. So what you are going to get is a positive number, 6,415.74, which is equals to VC square. Now, if you take the square root, you will basically get this, 6415.74 which is going to be equals to plus or minus 80.1 meter per second. Now, we are going to select the negative root, not the positive one. So V is equals to minus 80.1 meter per second. Why? Because the velocity of VC is pointing downward. So you can either write it this way, or you can say VC is equals to 80.1 meter per second, and you have to put the arrow downward. This replaces the negative sign. So in the end, what we just discussed the constant acceleration relation, which are V equals to V0 plus AC multiplied by T, S equals to S0 plus V0T plus half AC T square, or V square equals to V0 square plus 2 AC multiplied by S minus S0. Don't forget that you should always define what is your positive and what is your negative direction. That's all. Thanks a lot.